Welcome back to another video. And today I'm going to show you how to convert 4.375 to an IEEE 754 16-bit floating point with a 1-bit sign, a 4-bit bias exponent, with an 11-bit fraction, or as people refer to it as a mantissa, with a bias equal to 7. So that seems like a lot of information. Let's break it down. So it's going to have 16 bits, so it's going to have 16 ones and zeros. With a 1-bit sign, all a 1-bit sign does, it represents if the number is positive or negative. 0 means positive, 1 means negative. So 4 is going to be positive, so the 1-bit sign is going to be equal to 0. And then we're going to have 4 bits for the bias exponent, which means 4 zeros or 1s. And then everything else is going to be the 11-bit fraction or the mantissa. And it's going to be 11 bits, which represents the fraction. It's going to be either zeros or 1s, and the bias is 7. And we'll talk more about the bias right now. So that's a whole lot of information, but we could break this down into 4 easy steps to get the IEEE 754 16-bit floating point. So we could do step number 1, which is convert to binary. Convert to binary. When we say convert to binary, we want to convert this number to binary. The way we could do that is we could break it up at the decimal point. So right here, we can have the number 4 over here and the number 375 over here, and then we could convert each number by itself to binary, and then we could join them at the decimal point. So to convert a whole number to binary, you just keep dividing it by 2 until the divisor is 1. You'll see what I mean by that. 4 divided by 2 is going to be equal to 2, remainder 0. We only care about the remainder. And then we bring the 2 over here to divide it again by 2. 2 divided by 2 is going to be 1, remainder 0. The divisor is 1, so we're not going to divide it by 2 anymore, we're going to stop. And then we're going to use these numbers to make our binary number. So we're going to start at the bottom and move up to the top. So we're going to do 1, next is 0, next is 0. So that's going to be 4 as a binary number. And if you don't believe me, we can just check it. Everything is going to be binary, so it's going to be like powers of 2. So I'm going to start at 1, 2, 4. If the bit is 0, that means it's turned off, so we ignore it. So the 1 is turned off, the 2 is turned off, only the 1 is turned on, which corresponds to the 4, which that is our number we wanted to convert. So that's successfully converted. So now we're going to convert 0.375, but instead of dividing by 2, we're going to multiply by 2. 0.375 times 2 is going to be equal to 0.75. And then we only care about the leftmost part, and then whatever's not the left, we're going to bring it back over to multiply it again. 0.75 times 2 equals 1.50. We only care about the left side. Once everything to the decimal point is equal to 0, we're going to stop. So we're going to bring the 0.5 over. 0.50 times 2 equals 1.00. Everything to the left of the decimal point is 0, so we stop. And then we're going to use these numbers right here to make our binary. And from here we went bottom to top. For this one we're going to go top to bottom. So we could say 0, 1, 1. So that's going to be the decimal representation for 0.375. We could bring the decimal point down right here, and then we could just join our numbers. 100 is going to be 4, and then 0.11, not 0.011 is going to be equal to 0.375. So this right here is our binary representation. Let me see if I could write it a little neater. 100011. So that's step 1. Let's get started with step 2. Step 2 is going to be to normalize or convert our binary to scientific notation. Convert to scientific notation. Oh, I forgot the decimal point. And the way we do that, we want to move the decimal point so only one number is to the left of it. So we could do that by moving it over twice. So it's going to be 1.00011. All I did was move it over twice. So now it's right there. So now we're going to convert it to actual scientific notation. We're going to multiply it by 10, and then we're going to have 10 to whatever power we moved it to. In this case, we moved the decimal point over 2. So this is our scientific notation representation. Keep in mind this number equals this number. They're the same thing. So that's step 2. Now we can move on to step 3. Step 3 is just to calculate our bias exponent. And then I'll show you how to do that right now. Calculate biased exponent. If you don't know how to do it, it's okay because there's a formula to do it. So I'm going to write the formula over here. We could say biased exponent equals the exponent. When we refer to the exponent, we refer to the number 2. However many spots we moved it over, plus the bias. The bias we were given, which is equal to 7. So we moved it over 2 places, so it's going to be, the number 2 is going to be our exponent, and the bias equals 7. So our bias exponent is going to be equal to 9. But remember, it's computer science, so everything's going to be in binary. So we can convert 9 to binary the same way we did 4. So we're going to do 9 divided by 2 is going to equal 4, remainder 1. We only care about the remainder. And then we bring the 4 over here to divide it by 2 again. 4 divided by 2 is going to be 2, remainder 0. Bring the 2 back over. 2 divided by 2 is going to be equal to 1, remainder 0. Once we have the divisor equal to 1, we stop, we just bring it over. And then this right here is going to be used to make our binary number. Once again, we start bottom to top. It's going to be 1, 0, 0, 1. And that's going to be our binary representation of the number 9. And if you don't believe me, we could do it again. 1, 2, 4, 8. 1 is turned on. 2 is turned off because it's 0. 4 is turned off because it's 0. 8 is turned on because it's 1. 1 means on. 8 plus 1 equal to 9. So that's correct. 1001 is going to be your bias exponent. And then we know what the sign bit is. We talked about it a little bit before. Sign bit 0 is positive, and then 1 is negative. We know our number is 4.375, so it's going to be positive. So our sign bit is 0. So we actually got quite a bit of information now. That takes us to our next and final step, which is going to be step 4. And now we're going to build the IEEE 754. I'm just going to abbreviate floating point with FP. You may be thinking, but we're missing what the fraction is. And then I'll actually show you how to find the fraction right now. So the IEEE 754 floating point is going to have 16 bits. So it's going to be 1. That's going to be the sign bit. The first bit's always going to be the sign bit. So let's actually fill it out because we know what the sign bit is. The sign bit's going to be 0 because the number's positive. And then we're going to have 4 bits for the bias exponent. And we know the bias exponent is 9, or in binary is going to be equal to 1001 because we found that. And by the way, the problem tells us that the 1-bit sign with the 4-bit bias exponent, and then everything else is going to be the fraction. It's going to be 11 bits. So let me have 11 spots for it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then you may be wondering, how do you actually find the fraction? So remember this number up here, whether we convert it to scientific notation. Let's just copy it. Copy. And then we can put it right here. So let me paste it. Or if not, we could just write it by hand because it wants to be difficult. So we could do 1, 0, 1, 0, 0, 0, 0, 3 zeros, 1, 1. So this number right here is just this number up here. And all the fraction is, or the mantissa, is going to be everything to the right of the decimal. That's all the fraction is. So let's actually label it sign bit, biased exponent, or the fraction, or the mantissa. I think I'm spelling that wrong, but that's okay. And remember, the fraction is just everything to the right of the decimal, which would just be this. See if I can write a little neater, but it's not any better. This is just a number in scientific notation, and we just copied it down here. So we're just going to write everything to the right of the decimal. It's going to be 0, 0, 0. That's these 3 zeros right there. 1, 1. And then you may be wondering, what about everything else? Everything else we could just fill in with zeros. And that right here is our 16-bit floating point representation of the IEEE 574 number. And just to be sure, let's count the actual bits to be sure it's 16 of them. It'd be 1, 2, 3, 4, 5, So that's 5 right here, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's it. This is going to be our answer. Let's give it a nice little circle because this is computer science and math combined. If this helped you in any way or you just enjoyed watching it and following along, please consider subscribing to the channel.